Good evening and welcome to this Texas Instruments Australia webinar. Tonight we continue our 2023 VCE Specialist Mathematics series and we will be covering the topic Logic and Proof. My name is Emily and I'll be your host for this evening. Our presenter tonight is Peter Flynn. Peter is an educational technology consultant for TI Australia as well as a national T-Cubed instructor. He has been involved in mathematics education for over 30 years and has a wealth of experience in sharing his knowledge at both local and international conferences. Thank you for joining us tonight, Peter, and now I'll hand over presenter rights to you so you can get started.
Welcome to the VCE Specialist Maths webinar series. My name's Peter. Tonight we're doing some logic and proof. So this page is a notes page, and I've used the snipping tool to take an excerpt from the study design and paste it into this notes page. So this is the proof and number section of the study design for units 1 and 2 specialist maths. On our next page, here is a snapshot of the logic and algorithms section of specialist maths unit 1 and 2. And for specialist maths units 3 and 4, there's an area of study called discrete mathematics, and logic and proof has been included into the study design starting next year. So tonight's presentation, we'll have a look at some direct proof and counter examples, briefly look at truth tables, and look at mathematical induction. There's not a hell of a lot here in terms of assessment and examinations. It's more a little bit about jazzing up some worked examples and integrating TI-Nspire into the teaching and learning of logic and proof. So let's look at our first example. So we're looking at direct proof and the use of counter example here. And so we're asked to consider the set of numbers S of the form n squared minus n plus 41, where n is a natural number. So I take natural numbers to be the positive integers and 0. This is also a notes page. This object here is a math box, and it is accessed by in a notes application or notes page by pressing menu, 3 for insert, and then 1 or enter for math box. And you'll also note that the shortcut is Control M. Now inside this math box, you can type and make expressions, look mathematical. So that looks quite nice. And inside a math box, if I right click or control menu in there and go to math box attributes, what you can also do is you can select no calculation, which means that that object will remain as is. There'll be no calculations performed on it. And you'll also will note here that if I press control and then the catalog to go into the symbols template, you have all these lovely mathematical symbols at your disposal. So there, for example, is an element of, and so I've used that to create that object there. So that's a little bit of background about what I'm doing in terms of formulating the presentation. Part A asks us to prove that all elements of S are odd. And part B is asking us to show by use of a counterexample that not all elements of S are prime. So I'm going to toggle between this page and also a spreadsheet page, a list and spreadsheet page that I've prepared and is a little bit further on in the document. So we first of all want to look at the parity of this expression. And so here I've set up a spreadsheet, and column A, I've given it the variable name n. In this formula cell, I have devised the formula, and it is saying that we're going to form a sequence of numbers I'm going to call it K. The variable is K, and that sequence of numbers is going to be from starting at 1 and finishing at 41. Now, for example, if we wanted even numbers starting at 2 and finishing at 82, you could insert there 2 times and press enter, and then it'll overwrite, and you can see 2, 4, 6, 8, 10, etc. So I'll go back and go back to our original setup, like so. And we can scroll down 1, 2, 3, 4, 5, 6, 7, etc. We can also go Control 1, take us to the bottom of the spreadsheet. Control 7 takes us back up to the top. And Control G can take us anywhere we like. So if we say we want to go to cell B2, we go to cell B2. So there's a few little shortcuts. So we're looking at the parity. Now in column B, I have called column B even. In the formula cell, you can tell that N is what we call a variable reference because there's a little apostrophe or a little tick mark there just before the N in superscript form. So I've basically formed n squared minus n for all these n values. And so if you scroll down, we can see that they're all even. Now, of course, we're just talking about examples at the moment. We're not undertaking any sort of formal proof. We're sort of, in a sense, playing around with, well, in this instance, part of the expression, and then in the next column, the actual expression. So you can tell that the numbers in column C are basically the corresponding number in column B plus 41. And so we can see here that if we scroll down, they're all looking odd. And if we scroll to the end, that would be indeed the case. So we're using the spreadsheet just to give the students an opportunity to have a look at outputs and to start to get a bit of an understanding for the type of numbers that this expression is generating. But now it's time, of course, to do the formal proof. If we go to the next page, and again, this is a notes page, and you can actually set up the notes page to display solutions just like I've done here. So the way to think about this is to say, well, okay, we've got n squared minus n plus 41. So let's break it up into two parts, or think of it as two components. One being n squared minus n, and the other being the plus 41. And of course, what we can do is we can factorize n squared minus n as a product of two factors. So we can write the expression S as n times n minus 1 plus 41. And then we need to think about the parity of n by n minus 1. So either n is even or n minus 1 is even. So therefore, n squared minus 1, which equals n by n minus 1, is even because even numbers are a product of an even number and an odd number. So part of the expression for S, the part that's dependent upon n, is even. Then you add an odd number to an even number, you get an odd number. So therefore, n squared minus n plus 41 is indeed odd. So that's the direct proof for part A. We now go back and have a look at part B, and we're going to again make use of a part of the spreadsheet that I showed for part A. We're going to show by use of a counterexample that not all elements of S are prime. So if we move along, just before we get to the listen spreadsheet application or page, this page is saying that we can use the listen spreadsheet application or indeed the notes application for part B to explore the existence of a counterexample before adopting a more formal solution approach. So this is shown on the next 3 pages. So you can already start to see the teaching and learning trajectory here. It's using the technology to explore and have a play with the situation, you know, and that can also form part of conjecture formation, and then it's adopting the formal proof. So let's have a look now. We've discussed column A, column B, and column C. Let's have a look at column D. So column D I've called P factors, which is short for prime factors. And in the formula cell for column D, basically I've just typed in equals factor, open bracket C. Now notice here, this is a column reference. And what it's doing is it's determining a prime factorization of all the numbers that are in column C. And we have an extra column, column E, which I've called prime. And if I go to cell E1, I'm using a command called isPrime, which is in the catalog. So it would be a matter of pressing the catalog, pressing 1 for A to Z, and then, as luck would have it, we hit upon isPrime. Isprime of a number is the syntax. And basically what I've done here is I've said, let's go for isPrime of the number that's in cell D1. And then what I've done is I've performed a fill down. So let's see how that operates. So what I'll do is I'll remove the instruction. You can either type isPrime or you can get it from the catalog. So isPrime and then open bracket D1, press enter. Now obviously nothing's going to happen because if you like, I'm overwriting the situation, but we scroll back up to cell E1, then we press menu, 3 for data, 3 for fill. And what this will do is it will fill down column E. And it's just a matter now of using the down arrow on the touchpad. So we go all the way down. Because I know the problem, I know when to stop. So I'm going to stop there and press enter. And that's how you populate column E. Okay. Now, we scroll all the way up. So if we go Control 7, what we're going to do now is we're going to look at whether we've got prime factors all the way through or not. So in fact, we can do it via a lists and spreadsheet. We can also do it dynamically with a notes application. And so what we've got here is I've got in a notes page a slider for N. And to insert a slider into a notes page, it's just a matter of pressing menu and then 3 for insert and then number 5 for slider. And then a dialog box will appear and you just fill out the fields in that dialog box. This is a notes page. This is a notes page where we generate values of S for particular values of N. We look at the prime factorization of S and we look at whether that particular value of S is prime or not. So you get a true or a false outcome. So what we do is we click on this minimized slider, and what we're seeing is values for S. You can see that the factors are 1 in itself. And so we're dealing with prime numbers at the moment. And that's why we're getting that result true. Right, so it's continuing. And then we get up to a very interesting value, which is 41. And when we get to 41, the value of S is 1681, which turns out to be a perfect square. And so the factors of S are 41 and 41, so 41 times 41 or 41 squared. And in fact, that's the first value of n for which this expression is composite. And that's why you get that false output there. If you were interested and you continued on, n equals 42 is composite, and then it's prime again until you get to n equals 45, and then up to 50 again, where it's again composite. Okay, so it now remains for us to think about what we've actually done here. So we have found a counter example, and all you need to blow a proof up is indeed a counter example. So if we go back, I'll just find my page here. There it is on the next page. For the part B solution, to find a composite number, what we do, interestingly enough, we found that it blew up when n equals 41. And so we make use of that constant term 41. So if we consider n equals 41 and substitute n equals 41 into S, what we find is we get 41 squared minus 41 plus 41, which cancels, and which leaves us with 41 squared, or indeed 41 times 41, which is not prime or indeed composite. So that's a way of augmenting the formal teaching of proof and counterexample by using the TI-Nspire for exploration and, in a sense, to form conjectures and hopefully a better understanding of what the question entails and what sort of details are required to undertake the proof. Spend a little bit of time, not very much, on truth tables. So a table of rows and columns showing the truth value, which we denote T for true and we denote F for false. So a truth table is a table of rows and columns showing the truth value of every possible combination of the given statements represented by letters as operated by what are called logical connectives. So let's define what a logical connective now is. So a logical connective is a word, for example, and, or is another one, usually written as a symbol. So it's the upside down V for and. The fancy word is conjunction, that carries an instruction of logic on how to operate a statement or compound statement. So logical connectives can also be used to combine two or more statements to indeed form a new statement. And here are 5 examples of logical connectives that students will meet with their accompanying symbols. And I got all those symbols from pressing Control and then the catalogue. For example, there's the and there's the or, etc., etc. Okay, so we've got negation, which is not, conjunction, which is and, disjunction or the inclusive or, implication or conditional, which is implies, and double implication or biconditional, which is if and only if. We can use TI-Nspire to construct truth tables, and rather than using T and F, what we do is we use a 1 for truth or T, and we use a 0 for F or false. TI-Nspire also recognizes the command and for conjunction, and it also recognizes or for inclusive disjunction. And for negation, you can use 1 minus. And these can be done in a spreadsheet environment, which I'll detail on the following page. So what we're going to do is we're going to show you basically how to create this particular truth table. So columns 1 and 2 are your anchor columns. So the way you set it up is your first statement, which is denoted by P. You start off with 2 T's and then 2 F's. And then you alternate the T's and the F's for Q. So in other words, you've got your 4 combinations there. Both true, true, false, false, true, false, false. Column 3 is P and Q. And the way to think about this is that P and Q is true if P and Q are both true. Otherwise, P and Q is false. That's why you get T, F, F, F there. This is the negation. This is an alternative symbol for the negation symbol. So this is not P and Q. And so what the negation is going to do is anything that was true is going to turn it false, and anything that's false is going to be turned true. And so we get that set up. So let's see how this looks in a TI-Nspire list and spreadsheet application. So column A I've called P, and we've got true, true, false, false. Column B is Q, and it is true, false, true, false. Column C, I've given it the variable P and Q. Now notice there that I've used the underscore. Okay, so I've used the underscore. Now underscore is control space, and it basically joins up the P to the and the and to the Q. We wouldn't be able to call it P space and space Q. It's got to be joined. Okay, so if I navigate now to the formula cell for column C, I can remove what's already there, like so, just pressing the backspace. And I can say, well, all right, let's have P and Q, and we'll let it, or assign it. You can see the colon equals, we'll assign it to be A space and B, and press enter. And there we go. So P and Q true. So P and Q is true if P and Q are both true. And then we've got these 3 that are false. And then, as we talked about, the role of the negation is basically taking anything that's true and turning it false and vice versa. So in the formula cell for column D, I've expressed that as 1 minus column C. And in that way, we've ended up with the 0, 1, 1, 1, if I said 3 ones. So you can do the same for P or Q, and you can set up quite a few truth tables using TI-Nspire. I wouldn't overdo it. I'd probably do it 1 or 2 times, or with a couple of examples with the students. But then I think what they should be doing is they should be constructing truth tables essentially away from Nspire. But the other thing about this also is it's quite a nice demonstration tool as well, and it's dynamic. And if students understand the link between T and 1, F and 0, then I think it's quite a nice way to introduce truth tables. So that's the second part of tonight's presentation. And the third one is we'll have a look for a few moments at mathematical induction. And what I've done is I've split this question up, which essentially is a 1-part question, into 2 to bring in the possibility of using TI-Nspire to form a conjecture. So here's our proof by induction starter anyway. Part A is saying, given that y equals 1 on 1 plus x, conjecture an expression for the nth derivative, dny dxn, for all positive integers. Now, if I go into our symbols again, control catalog, what you'll find is if I navigate up and across, there's your quantifiers. So there's your for all, and there's your there exists. So I think that the symbols palette here is quite extensive. And as I said in a previous comment, it can be used to produce correct mathematical symbolism and conventions and notation to help you. Basically, I'm not moving from the Nspire environment to PowerPoint or anything like that. I'm doing everything within Nspire. So I think that that's an ease of use that I would like us as teachers and also mentors for teachers to be more cognizant of in the years ahead, that we can do way, way more inside this platform than what we think, even what the experts think. Okay. So here's an opportunity again to explore. And we can use the lists and spreadsheet application or the notes application to explore indeed the first few derivatives of y before embarking upon the formal induction proof. And this exploration is shown in the next 2 pages. So we've got a list and spreadsheet page or an application, and we've also got a notes application. So let's have a look first of all at the lists and spreadsheet application. And what I've done in column A is I've given it the variable reference n. Again, I've set up that sequence. You can just type in SEQ for sequence, and basically I'm just saying n is 1, 2, 3, 4, 5, 6. We're just looking really at the first 6 derivatives. You can certainly extend this spreadsheet if you wish. Column B I've called derivs, and in cell B1 what I've done is I've pressed catalog, and then I've gone to number 5, the symbols templates, and I have identified and used the nth derivative template. And if you have a look down here at the formula, what I've put in instead of n is I've put in A1, right? So in this cell, I've typed in equals, then I've used the nth derivative template, and there's a space there, and I've put in A1, and then open bracket, and then our expression for y, which is 1 on 1 plus x, and pressed enter, and that's given us our first derivative. And then what I've done is I've highlighted that cell and filled down like I showed you before. So to fill down, it's menu, data, and then 3 for fill. So if I scroll down one, and if you have a look at what's happening in the, if you like, the entry line below, this is the second derivative of y with respect to x. This is the third, this is the fourth, this is the fifth, and this is the sixth. And what I've also done, now I know you can see the answer here, but you can build this up with the students. I would first of all get the students to have a look at what's happening to the coefficient there each time. I wouldn't worry too much about the x plus 1 to the power bit. So what's happening is, first of all, we've got a change of sign. So that's one thing you can notice. You've got to frame questions, to the students. What do you notice? What can you see? All right, so we see a change of sign. We also see these numbers, and I'm forgetting about the sign for a moment, 1, 2, 6, 24, 120, 720. Have you ever seen those numbers before? So hopefully they can twig that they've got a sign changer and they've got some factorials happening. So you say, well, okay, can you build a formula which will give us the coefficient for each successive derivative? So we want a sign changer. So in column C, I've called it coefficient. You can get students to see if they can develop the formula themselves. So it's a bit of trial and error. The first bit is to try and work out, well, how do I get a sign changer? Well, -1 to the power of n, that's a good sign changer. And then multiplied by n factorial. So I've put that formula, or it's the upshot of a discussion. That's the formula that goes into the formula cell for column C. And what we're doing is we're generating each successive coefficient. So that's quite good. Then we can concentrate on what's happening apart from the coefficient. So what we see is each time we've got an x plus 1 term, it's in the denominator, and if you like, we're in the denominator, the power is increasing by 1 each time, and the power is 1 greater than the n value that's in column A. So we can speculate here that the formula for the nth derivative is, if I can jump ahead before discussing the notes application, the nth derivative of y with respect to x, given that y equals 1 on 1 plus x, we can conjecture that it's equal to -1 to the power of n by n factorial on 1 plus x to the power of n plus 1 for all positive integers. We can also do this. So just one other quick point, go back to the spreadsheet. What's really interesting about this spreadsheet is you might have thought that it's just numerical, but in fact, it's algebraic. The spreadsheet is algebraic, or can be algebraic. So I think that that's a really, really powerful feature. If I'm going to be honest, I don't like the way that that is written, but at least you can see there the coefficient and the behavior of the x plus 1. So we can use the notes application to do the same thing and to get a much nicer output for these successive derivatives. So if we go now to a notes page, which this is just typing in text. So I've just typed in nth derivative generator. This is a math box. And so a math box, to insert a math box, you press Control M or go through the menu. And I've just assigned y to be 1 on 1 plus x. So the input is blue and the output is green. I've inserted a slider. Here is another math box where I've used the nth derivative template. And basically, this slider is going to act as a counter. So as I change the value of n, we're going to get successive derivatives appearing here in this math box. And, I've been quite opaque here. I've been quite transparent here and just offered the formula. I could have been opaque and hidden that input, but it's there. All right, so these three math boxes, if I go in and then right click or control menu for math box attributes, that's show input and output. And you can choose, you can have hide input, hide output, or no calculation. So Sometimes it's really useful to hide the input and just show the output. And you saw the advantages of that back when we were looking at the expression for s, n squared minus n plus 41. So I'll press escape. So now it's time to make contact here with the slider button. What we currently have, obviously, is the first derivative. And so now let's look at, here's the second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative. Okay, so it's basically mimicking what we saw in the spreadsheet. The advantages of the spreadsheet is that you see successive derivatives in a column. Here what you're doing is you're watching, well, this is another way of doing it, is watching how the particular objects change in the expression as you change the value of n. So we've formed the conjecture, and now it's time to do the formal mathematical proof by induction. Now, look, to be honest, in an exam, I don't think you're going to get, not that I know, and I'm not part of the VCEE, but I don't think, I mean, you've got to be really careful with asking students for conjectures in exams. I suppose it's possible, but it's much more likely that students will be asked to answer this question using induction. Great thing about teaching and learning is you can use the Nspire to undertake a conjecture. So we know quite a bit about how these successive derivatives are behaving before we get to the question. Okay, so this looks like an exam 1 question to me. Interestingly enough, I suppose, if it was set in exam 2, students at least could differentiate and check the result for n equals 1. I mean, that's possible, but it wouldn't be a very good idea on time grounds. So part B, given that y equals 1 on 1 plus x, prove by mathematical induction that the nth derivative dny dx dx of n is given by -1 to the power of n by n factorial on 1 plus x to the n plus 1 for all positive integers. So now it's time to look at the formal proof, and induction basically consists of 3 steps. There's first of all the base step, then there's the inductive step, and then there's the concluding or conclusion step. So because we're looking at n being positive integers, our base step, we first check that the result is true for n equals 1. And so we look at the left-hand side, and the left-hand side, dy dx is -1 on 1 plus x squared. And the other thing with the base step, what you've got to hammer into students is they've got to look at the left side and they've got to look at the right side. It's not good enough to just look at one side. And so the right-hand side is substituting n equals 1 into the given result. And depending upon the marking scheme, so I can't make any comments on this, I'd be encouraging students to show you and to show the examiner this. So this is substituting n equals 1 into it and then showing that it equals or simplifies to -1 on 1 plus x squared. So indeed, the left side equals the right side, so it's true for n equals 1. So don't gloss over that step. That's very important. Let's go to the inductive step now. And it's really important that the assumption of truth is apparent. So we assume true for n equals k, hammer into the students that is the exact way they should be stating the inductive step. Don't be messing around with let n equal k or assume n equals k is true and these sort of variations. Assume it's true for n equals k. In other words, that the kth derivative of y with respect to x is equal to that. So in other words, it's just wherever you see n, it's substitute for k. And now we consider n equals k plus 1. And so the k plus 1th derivative, what we do is we take the kth derivative and we differentiate it. That's basically what's going on there. So we substitute in for the kth derivative into this line here. So this is typing, and if I just click on this, you know, this is an image, and it's from the snipping tool. It's just been imported into a notes page. So again, this is good for demonstration purposes. You don't have to write this out on the board. You can talk your way through it, and hopefully the students can follow what's going on. So to go from this line to this line, -1 to the power of k times k factorial, that's a constant. So we can bring that out the front. And then it's a matter of differentiating 1 on 1 plus x to the power of k plus 1. Constant hangs out the front. And when we differentiate, the power comes out the front. So it's negative times k plus 1 times 1 plus x to the power of negative k plus 2. Be careful with the brackets. Be careful with the negative signs. So this negative here can be incorporated into this negative in here to form -1 to the power of k plus 1. In other words, -1 to the power of k by -1 is -1 to the power of k plus 1. K factorial times k plus 1 gives you k plus 1 factorial. And then we write the 1 plus x to the power of k plus 2 as a denominator as part of the expression. Now that looks very nice. That looks exactly what we should end up with. Okay. So we've completed the inductive step, and then students get excited and move on to the next question. And I don't know what the VCEE marking scheme is going to be for these, but I do have some insight into the IB, where induction has been assessed for a number of years. And in the IB, there's a mark awarded for the concluding step. So it's really important to get the concluding step right and to get the logic right. So we assumed it was true for n equals k. So if it's true for n equals k, then it's true for n equals k plus 1, which we've proven. And since we demonstrated that it was true for n equals 1, we can therefore say that the nth derivative of y with respect to x, given that y equals 1 on 1 plus x, is indeed equal to that. Okay, so that pretty much completes my presentation for this evening. There is a bit more to do with the TI-Nspire in the area of study of discrete maths and also the topics of logic and proof than one possibly meets the eye. It's just a matter of teasing it out. So when you're considering your worked examples in this area of study, say to yourself, can I use the TI-Nspire for any sort of exploration, for any sort of conjecture? And they are the introductory sort of activities and mathematical thinking that leads into direct proof, proof by contrapositive, proof by contradiction, counterexamples to blow up proofs, and also proof by induction. So that's it from me. I'll hand it back over to Emily. So thanks very much for your attention, and we'll catch you next time. So thank you very much.
Thank you, Peter. Thank you for that wonderful presentation. I note that some people in the chat are asking where you can get the recording. That will be on our YouTube channel. There is a link to that in the chat. It does take a couple of days to get back up, but it will be there. It will also be on our website. Just having a look.
Emily, I'll also provide you with... sorry, Emily, sorry. I'll also be able to provide you with the TI-Nspire file that I've showed this evening as well. So hopefully participants can get access to that as well.
Yes, yep. There'll be a follow-up email, so just a thank you for attending email, which will contain Peter's files, as well as a link to your PD certificate for attending tonight. Okay. Don't think we have any more questions. Thanks again, Peter, and I hope everyone has a lovely night.
Thanks, Emily. Good night, all.